Hello, I am Dr. Srinivasa, Associate Professor and Head of the Department of Physics in Government First Grade College, Tirtu, belongs to Tumkur University. In this video, I am going to do the video class on units and measurements prescribed by the Tumkur University for the paper Mechanics and Properties of Matter for first B.Sc. first sem students. So the unit 1, the name of the unit is Basics of Mechanics and the chapter is Units and Measurements. The learning objectives of this video are dimensions of physical quantities, dimensional formula, dimensional equation and dimensional analysis, also different types of dimensional formula. Prerequisites to do this video are what are physical quantity, different types of physical quantities, what is a unit, different types of units and system of units. The session outcomes. From this session, students will be able to understand what are dimensions of physical quantities, what is dimensional formula, what is dimensional equation, what is the use of dimensional analysis, and also able to write dimensional formula of different physical quantities. So, first of all, dimensions of a physical quantities. Dear students, we know that the nature of a physical quantity is described by its dimensions. So, all physical quantities can be expressed in terms of the dimensions such as length, mass and time. All the physical quantities can be expressed in terms of the 7 base or fundamental quantities, namely mass, length, time, electric current, temperature, intensity of light and amount of substance raised to some power. Then, the dimensions of a physical quantity are the powers or exponents to which the fundamental or base quantities are raised to represent that quantity. That means the dimensions of a physical quantity is defined as the powers to which the fundamental or base physical quantities must be raised to get the physical quantity of that unit or unit of that physical quantity. So here is a note. The dimensions of a physical quantity are represented by the square bracket around a quantity, means that we are dealing with the dimensions of the quantity. For example, the dimensions of volume of an object are V is equal to length into breadth into height. So the dimensions of length, length is L and the symbol of breadth is also L and height is also represented by L. So L into L into L gives the L cube in a square bracket. So square bracket L cube, close this square bracket, gives the dimensions of the volume. Similarly, the dimensions of force are square bracket m raised to the power 1, L raised to the power 1 and T raised to the power of minus 2 and the closing square bracket. Similarly, the dimensions of energy are also represented by m L square T to the power of minus 2. Therefore, dimensions of a physical quantity is defined as the powers to which a physical quantity must be raised to get the physical quantity such as force, energy and velocity. And also using these dimensions we can write the unit of a given physical quantity. This is the main importance of the study of dimensions. Dimensional quantity. So there are some physical quantity having dimensions and some other physical quantity don't have dimensions. So dimensional quantity is a physical quantity which has dimensions. That means the physical quantity which are having dimensions are called dimensional physical quantities. For example, speed, velocity, acceleration, momentum, torque, energy, etc. etc. These are all physical quantities having dimensions. Similarly, dimensionless quantity. Dimensionless quantity is a physical quantity which has no dimensions. Certain physical quantities which don't have dimensions are called dimensionless quantities. For example, relative density, refractive index, strain, etc. Because these are only ratios. When the physical quantities having ratios, their dimensions get cancelled each other. For example, refractive index or absolute refractive index is defined as ratio of velocity of light in free space to the velocity of light in a medium. So both are velocities. The dimensions of velocities are get cancelled. Therefore, they don't have dimensions. Similarly, dimensional constants. Dimensional constant is a constant which has dimensions. Certain constants have dimensions. They are called dimensional constants. For example, universal gravitational constant, Planck's constant, Hubble's constant, Stefan's constant, Wien's constant, Boltzmann constant, etc. are having dimensions. Therefore, they are called dimensional constant. Dimensionless constants. Certain constants which don't have dimensions, they are called dimensionless constant. So, dimensionless constant is a constant which has no dimensions. For example, 5, minus 0.38, exponential, pi, etc. They don't have dimensions. Dimensional formulae and dimensional equations. So, all physical quantities can be expressed in terms of the powers must be raised by the physical quantities or the fundamental physical quantities. The expression which shows how and which of the base quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. The expression which shows how and which of the base quantities or fundamental quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. An equation obtained by equating a physical quantity with its dimensional formula is called the dimensional equation. An equation obtained by equating a physical quantity with its dimensional formula is called the dimensional equation of the physical quantity. All dimensional formula are expressed in terms of the fundamental physical quantities or base quantities such as mass, length and time raised to some powers. So you already know that the example of dimensional formula, that is dimensional formula of the volume is V is equal to, so volume is defined as length into breadth into height. So length, breadth and height are represented by the formula L. So L into L into L gives L cube. So L cube is the dimensional formula for volume. So volume is equal to L cube. Volume is a physical quantity and L cube is the dimensional formula. Physical quantity equated with the dimensional formula is called dimensional equation. That is, V is equal to L cube is the dimensional equation. Similarly, we can write the dimensional formula of speed or velocity. So we know that velocity is defined as rate of change of displacement. That means velocity is equal to displacement over time taken. Displacement is represented by the dimension L and time is represented by capital T. So all dimensions are represented between the square bracket. So square bracket of L t to the power of minus 1 is the dimensional equation of the velocity. All dimensions are represented by the three fundamental physical quantity of length, mass and time. Here the dimensional equation of the velocity is given by m raised to the power of 0, l raised to the power 1 and t raised to the power of minus 1. So m 0, l t to the power of minus 1 is the dimensional formula of velocity. Here m to the power 0 represents that the measurement of velocity does not require the measurement of its mass. The dimensional formula of acceleration is written as, you know that acceleration is defined as rate of change of velocity. Therefore, acceleration is equal to change in velocity over time taken. We already know that the dimensional formula for velocity is L power 1 t to the power of minus 1 and time taken is represented by t, that is equal to L t to the power of minus 2, and all dimensional formula are represented by m, L and t. Therefore, it can be represented by m to the power of 0, L t to the power of minus 2. So, the dimensional formula for acceleration is m power 0, L power 1, t to the power of minus 2. Similarly, we can write the dimensional formula for momentum. We know that momentum is equal to product of mass and velocity. It is a mass, it is not t, mass into velocity. So, mass is represented by capital M and velocity is represented by L to the power minus 1. So, m power 1, L power 1 and t to the power minus 1 represents the dimensional formula for momentum. Similarly, we can write the dimensional formula for force using the formula F is equal to ma. Mass is represented by m and acceleration is represented by L t to the power of minus 2. Therefore, m L t to the power of minus 2 is the dimensional formula for force. So, we already know that what is dimensional equation. Dimensional equation is represented by a physical quantity equated with its dimensional formula. So, volume V is equal to m to the power of 0, L cube t to the power of 0 represents the dimensional equation of the volume. Similarly, velocity, etc., etc. Dimensional formula and dimensional equations continues. Okay. Dimensional analysis and its applications. Why we have to study the dimensional formula and dimensional equation? Dimensional analysis can be used to check the dimensional consistency of equation using the principle of homogeneity of dimensions. And also it is used to convert units in one system into another system. And the third one, it is used to derive the relation between physical quantity based on certain reasonable assumptions. So, dimensional analysis can be used to check the dimensional consistency of equation, to convert one system of units to another system, and also to derive the relation between physical quantity by assuming certain assumptions. The first use is that checking the dimensional consistency of equation. To check the dimensional consistency of equation, we have to know the principle of homogeneity of dimensions. What is the statement of the principle of homogeneity of dimensions? So we know that the magnitudes of physical quantities may be added together or subtracted from one another only if they have the same dimensions. This is important. The magnitudes of physical quantities may be added together or subtracted from one another only if they have the same dimensions. That is, all the terms on both sides of the physical equation must have same dimensions. Then only we can add or subtract or multiply. If all the terms on both sides of the physical equation must have the same dimensions, it is called principle of homogeneity. For example, initial velocity can be added to or subtracted from final velocity because both are velocities. because they have same dimensional formula m to the power of 0, L to the power of 1, T to the power of minus 1. But force and momentum cannot be added because they are different physical quantities and they have different dimensions because their dimensional formula are different and are given by the dimensional formula for force is m L to the power of minus 2 and for momentum m L to the power of minus 1 respectively. So, example, to check the dimensional consistency of the physical equation V square is equal to U square plus 2AS. First of all, we should check whether the dimensions of a physical quantity on either side of the physical equation must be same or not. Then only we can write this equation is correct. That here V is the final velocity and U is the initial velocity and A is the acceleration, S is the displacement or distance travelled. The dimensions of the quantities involved in the equation are U, the initial velocity is represented by m power 0 L to the power of minus 1. You already know that the dimensions of a velocity. Similarly, the final velocity is also the same, m to the power of 0 L to the power of minus 1. The dimensional formula for acceleration is m to the power of 0 L to the power of minus 2. And the displacement is represented by m to the power of 0 L and t to the power of 0. Substituting all these dimensions in the above equation, we get, so V square m to the power of 0 L to the power of minus 1 whole square. Similarly, for U square, same, plus. So acceleration is represented by the dimensional formula m to the power of 0 L to the power of minus 2. And the displacement is represented by m to the power of 0 L to the power of 0. Here the 2 is a number that has no dimensions. So m to the power of 0 L square t to the power of minus 2 by squaring this equation. So m to the power of 0 L into square, L into L is L square, t to the power of minus 1 into 2, t to the power of minus 2. So similarly same plus here m power 0, the product is m power to the power of 0 only. L into L gives L square, t to the power of minus 2 into t to the power of 0. We are adding the powers of the t, so t to the power of minus 2. Here on either side of the physical equation, they have the same dimensions. Therefore, this equation is dimensionally correct. That is, V square is equal to U square plus 2AS has the same dimensions on either side of the physical equation. Therefore, this equation is dimensionally correct. Each term of the above equation has same dimensions. Therefore, the given equation is dimensionally correct or dimensionally consistent. Here, the constant 2 in term 2AS does not have dimensions. Therefore, we are omitted the 2 term in this equation. Second one, conversion of units in one system into another system. The second use of the dimensional analysis is that conversion of units in one system into another system. Units are derived from the dimensions and the dimensions are derived from the actual formula of physical quantities. So, we can obtain the units from the dimensions and also from the units we can also obtain the dimensions of a physical quantities. If the dimensions are known for a physical quantity, then it is easy to express its FPS, CGS and MKS, even as a system of units also. By knowing the dimensions of a physical quantity, we can write the units of that quantity in CGS, FPS, MKS or SS system. Okay, we already know that N1 into M1 raised to the power A, L1 raised to the B, T1 raised to the power C is equal to N2 into M2 raised to the power A, L2 raised to the power B and T to the power of C. We can obtain the relation between one system into another system. So N1 and N2 are the magnitudes in the respective systems of the units, and M1, L1, T1 is the fundamental physical quantities in one system of units, and M2, L2, T2 are the fundamental physical quantities, dimensions of the fundamental physical quantities in the other system of units. From this formula we can write equal for N2. Here from this formula we can find the relation between one system and the other system. So let us obtain the relation between N2 and N1. So N2 is equal to N1 into M1 by M2 raised to the power A, L1 upon L2 raised to the B, T1 upon T2 raised to the power C. So we already know that N1 and N2 are the magnitudes in the respective systems of units. So smaller the unit, bigger the magnitude of a physical quantity and vice versa. So using this relation, we can obtain the relation between the two systems of units. M1, L1, T1 are the fundamental physical quantities in one system of units, and M2, L2, T2 are the fundamental physical quantities in the other system of units. So using that relation, we can convert 1 joule into erg. So 1 joule is the unit. Joule is the unit of energy or work in SS system, and erg is the unit in CGS system. So we already know that joule is the S unit of energy or work, and erg is the CGS unit of energy. We already know that the dimensional formula of energy or work is M L square T to the power of minus 2. The units from dimensions in SI and CGS systems are kg for mass, kg for length, meter, so L square, meter square, for time, second, so T to the power of minus 2, S to the power of minus 2. And the units of mass in CGS is gram, length, centimeter, the unit of length in CGS is centimeter, so L square, centimeter square. The unit of time is also second, so S minus 2 respectively. So kg meter square, kg, meter and second are the units of mass, length and time in SI system. Gram, centimeter and second are the CGS units of mass, length and time. Let M1 joule is equal to N2 erg. We have to obtain the relation between the joule and the erg from SI and CGS system. So M to the power of A, L to the power of B, T to the power of C is the dimensional formula. So the dimensional formula of work or energy, they have the same dimensions, is equal to M L square T to the power of minus 4. This is the general dimensional formula having exponents A, B, C. Here the M to the power of 1, L to the power of 2, T to the power of minus 2 are the powers to the mass, length and time. Compare this equation, we will get the values of A, B and C. Here M to the power of A, M to the power of 1. So A is equal to 1. So L to the power of B and here L square. So B is equal to 2. Here T to the power of C and T to the power of minus 2. So C is equal to minus 2. Using these dimensions equations, we get the powers A is equal to 1, B is equal to 2 and C is equal to 2. So in the table, we can give all this for units of mass, length and time in SI system and CGS system. Here if you take magnitude N1 is equal to 1 because 1 kg, 1 meter and 1 second. So what are the magnitudes of N2 we have to find out. So in SI system, the unit of mass is kg. So 1 kg is equal to 1000 gram, you already know that. So the unit of length is 1 meter. So 1 meter is equal to 100 centimeter. Unit of time is 1 second. Similarly, the CGS unit of mass is gram. The CGS unit of length is centimeter. CGS unit of time is second. So we are not A is equal to 1, B is equal to 2 and C is equal to minus 2 from this equation. Putting all these values in the relation obtained in the last slide, N2 is equal to N1, M1 by M2 whole to the power of A, L1 by L2 whole to the power of B and T1 upon T2 whole to the power of C. Substitute M1, M2, L1, L2, T1, T2 and the values of A, B and C in this equation. We will get the value of N2. So N2 is equal to N1 is 1 here, N1 is equal to 1 and M1. So the mass in kg in SI system and it is converted into 1000 gram. So M1 is equal to 1000 gram and M2 is 1 gram. Similarly L1 is 100 centimeter. So 1 meter is converted into 100 centimeter and this L2 is 1, L1 is 100 centimeter, L2 is 1. Similarly the units of time in both the units are second. So 1 second, 1 second. So here power A is equal to 1, B is equal to 2 and C is equal to minus 2. So gram, gram, centimeter, centimeter, second, second get cancelled. So N2 is equal to 1 into here 1000, 100 square into 1 minus 2. So 100 square is 10 to the power of 4, 10 to the power of 4 into 10 cube is 10 to the power of 7 into 1. So N2 is equal to 10 to the power of 7. 1000 can be written as 10 cube and 100 square can be written as 10 square whole square 10 to the power of 4. 10 cube into 10 to the power of 4 gives the 10 power 7. So from this relation we get the N2 value as 10 power 7 or 1 joule. Substitute in the value of N2 in this equation. So N1 is 1. So 1 joule is equal to N2 is 10 to the power of 7. So 10 to the power of 7 erg. So we are getting the relation between one system of units to another system of units. That means to convert erg into joule, we should write 1 joule is equal to 10 to the power of 7 erg. So using the dimensional analysis, we can obtain the relation between one system of units to another system of units. Second application is that to convert 1 Newton into a system where mass is measured in mg, length in kilometer and time in minute. So Newton are represented by mass into acceleration. For mass kg, acceleration meter per second square. So Newton can be written as kg meter per second in unit of force in SI system and milligram kilometer minute minus 2 is the unit in the new system. So the dimensional formula for force is ml to the power of minus 2. Similarly, let N1 Newton is equal to N2 milligram kilometer minute minus 2. You already know how to convert one system of units to another system of units. That is N2 is equal to N1, M1 by M2 power A and L1 upon by L2 B, T1 upon by T2 whole to the power of C. So as in the last slide, the in SI system, the unit of mass is kg. If we convert it into milligram, 1 kg is equal to 10 power 6 milligram. Length 1 meter is equal to 1 by 1000 kilometer because 10 to the power of minus 3 kilometer. So 1 second is equal to 1 by 60. In N2 new system, we have to find out N2 1 milligram 1 kilometer. Here they have given milligram, kilometer and minute. So second can be converted into minute. So 1 by 60th of the second actually. M power A, L power B to the power C is equal to M L to the power of minus 2. This is the dimensional formula for force. Compare these two equations. You will get A is equal to 1, B is equal to 1 and C is equal to minus 2. Substitute all the values of m1, m2, l1, l2, t1, t2 and with the values of a, b, c in this equation we get. So m1 is equal to 10 to the power of 6 and m2 is 1 milligram. So l1 is equal to 1 by 1000 kilometer divided by 1 kilometer. Similarly, t1 is 1 by 60. So t2 is 1 second. Milligram, milligram, kilometer, kilometer, second, second, get cancelled. So simplify this equation, we get n2 is equal to 10 to the power of 6. So 1 by 1000 means 10 to the power of minus 3 into 1 by 60. 60 whole square will get, and 60 whole square is represented by 3600. So 3600 into 10 power 6 into 10 power minus 3 gives n2 is equal to 3.6 into 10 to the power 6. On simplifying this value, you get n2 is equal to 3.6 into 10 power 6. Substitute the value of n2 in this equation, you get 1 Newton is equal to, the n2 value is 3.6 into 10 power 6 milligram kilometer per minute square. The third use of dimensional analysis is that deducing the relation among the physical quantities. How to derive an equation using the dimensional analysis. The method of dimensions can sometimes be used to deduce relation among the physical quantities. For this, we should know the dependence of the physical quantity on other physical quantities. Up to 3 physical quantities are linearly independent variables. So we are taking only the product of 3 or more linearly independent variables and consider it as a product type of the dependence. We can derive the physical equation if the physical quantities are of product type. This is one of the limitations in this use. For example, derive the time period of the simple pendulum. This is one of the example how to derive a physical equation. The time period of a simple pendulum. Consider a simple pendulum having a bob attached to a string that oscillates under the action of the force of gravity. Suppose that period of oscillation of the simple pendulum depends on its length, L, mass of the bob M, and acceleration due to gravity G. If we consider the oscillation of the simple pendulum under the action of the gravity, so the simple pendulum gets having the bob attached to one end of the string and the other end of the string is connected to the stand. If the simple pendulum oscillates in the gravity, so the period of the simple pendulum, that is time required for one complete oscillation, it depends upon the length of the simple pendulum, mass of the bob, and also acceleration due to gravity. Derive the expression for its time period using methods of dimensions. So the dependence of time period t on the quantities L, G and M as a product may be written as time period t is equal to some constant k, L to the power of x, M to the power of y, Z to the G to the power of z. So t is equal to k, L to the power of x, M to the power of y, G to the power of z. We should find out the values of x, y and z using the dimensional formula of time period, where k is a dimensional constant and x, y and z are the exponents. The dimensions of the quantities involved in the equations are, so mass is represented by m, L to the power of 0, T to the power of 0, L, M to the power of 0, L to the power of 0 and G is the acceleration due to gravity. Acceleration due to gravity and acceleration have the same dimensions. So M to the power of 0, L to the power of minus 2. So the dimensional formula for time t is M to the power of 0, L to the power of 0, T. Substitute all these values in this equations. We get by t is equal to k l to the power of x, m to the power of y, g to the power of z. So for time, dimensional formula like this, and k is a constant, length, the dimensional formula for length, dimensional formula for m, and dimensional formula for acceleration. So m to the power of 0, l to the power of 0, t is equal to, here m to the power of y only is there. There is no x term, there is no z term, only m to the power of y from this formula. And here l to the power of x, here l to the power of 0, there is no y term, here l to the power of z is there. So for l, x plus z, l to the power of x plus z, here t to the power of 0, there is no x term, here t to the power of 0, there is no y term, so t to the power of minus 2, or to the power of z, so t to the power of minus 2 z. So compare the values of y, x and z on either side of the physical equation. And equating the dimensions on both sides, we have y to the power of 0, there is here y, m to the power of y, m to the power of 0. So y is equal to 0, l to the power of x plus z, l to the power of 0. So x plus z is equal to 0. Similarly, minus 2z is equal to 1. T to the power of 1 is there, minus 2z is equal to 1, so z is equal to minus of. Minus 2z is equal to 1, z is equal to minus of. Substitute the value of z is equal to minus of in this equation. X minus of is equal to 0, so x is equal to off. So we get x is equal to off, y is equal to 0, and z is equal to minus 1. Substitute all the values of x, y, and z in the above equation. T equals k, l to the power of x, m to the power of y, g to the power of z. We get t is equal to k into l to the power of x, x value is half, l to the power of y to the power of 0. Therefore, there is no mass term. So g to the power of z value is minus of, so g to the power of minus of. We can write this equation as, so for half we can write square root, t is equal to k into l to the, so l to the power of g to the power of minus of, g come downwards, so t is equal to k into root of l by g. The value of k is 2 pi and determined from the other methods. We cannot find the proportionality constant using the dimensional analysis, but we can obtain the value of k from other methods. The value of k obtained from the other methods is 2 pi. Substitute the value of 2 pi in this equation, get t is equal to 2 pi into root of l by g. So using the dimensional analysis, we can derive the relation between physical quantities. So this is one of the important application. Demerits of dimensional analysis. The dimensional analysis cannot be used in the following cases. First one, the value of constant in an equation cannot be determined as the constant do not have dimensions. So as in the earlier slides, the k value cannot be determined using the dimensional analysis. It is not possible to determine the value of proportionality constant, so using the dimensional analysis. Second one, only dimensional consistency and not the physical consistency can be tested. We can test only dimensional consistency. If two half squares are there, that physical consistency cannot be tested. Dimensions can be formed from the physical quantity, but physical quantity cannot be always guessed from dimensions, because two or more quantities may have same dimensions. For example, energy and work, like that, stress and force, etc. etc. The equation containing the dependency on more than 3 quantities cannot be determined using only ML and T. If the dimensional equation having more than physical quantities such as length, mass and time, we cannot derive that equation. If 4 independent quantities are involved, then 4 variables and then 4 simultaneous equations are required. Hence there must be 4 fundamental dimensions. The equation containing exponential, trigonometric, logarithmic functions, etc. cannot be derived as they do not have dimensions. The equation containing exponential, trigonometric, logarithmic functions, etc. cannot be derived as they do not have dimensions. So, using dimensional analysis, we cannot identify all these values. The equations having the relations other than products or quotients cannot be derived. This is also one of the important limitations. The equations having the relations other than products or quotients cannot be derived. If the equation contains addition or subtraction, plus or minus sign, those equations cannot be derived using the dimensional analysis. Some dimensional formula of physical quantities. So you already know that length, the symbol is L, fundamental formula is a fundamental L. So dimensional formula is m0 L to the power of 0. We can write the unit using the dimensional analysis. The unit of length is meter, mass kg, time a second, area length into breadth. So n into L square. So m power 0 L square to the power of 0 is dimensional formula of area. So meter is the unit of length. So meter square is the unit of area. Similarly, meter cube is the unit of volume. Linear density is defined as mass per unit length. So for mass m, length L, so L to the power of minus 1. So m L minus 1 to the power of 0 is the dimensional formula of linear density. The unit of mass is kg. The unit of length is meter. So L minus 1, meter minus 1. So kg per meter is the unit of linear density. Similarly, we can obtain the dimensional formula for mass density, specific gravity, specific volume, time period, frequency, etc. etc. So frequency nu is equal to 1 by t. So m to the power of 0, l to the power of 0 by t. So m 0, l 0 to the power of minus 1 is the dimensional formula for frequency per second, or Hertz is the SI unit. Similarly, the dimensional formula for work is symbol is W. Work is equal to force into displacement. So m L square to the power of minus 2 is the dimensional formula, and kg meter square per second or joule is the SI unit. So work and energy are the same unit and same dimensional formula. Energy density is represented by energy by volume. So this is the dimensional formula, and joule per meter cube is the unit. Similarly, power. So power is work by energy, work or energy by time. mL square to the power minus 3 is the dimensional formula. Joule per second or watt is the SI unit. Similarly, we can obtain the dimensional formula for power, pressure, gravitation constant, universal gravitation constant, intensity of gravitation, etc. etc. Using these formula, these are the dimensional formula and these are the SI units. And this table gives the dimensional formula and units of the different physical quantities. And this is another table gives the dimensional formula and units of stress, strain. So strain has no dimensional formula and also unit because it is a ratio. And modulus of velocity, all modulus of velocity have same units and same dimensional formula. Poisson ratio is a ratio, don't have dimensional formula and units. Similarly, surface tension, surface energy, coefficient of viscosity. So all these having dimensional formula and units like this. This table gives the dimensional formula of and SI units of heat coming under the chapter heat. These are the reference books I have used to do this video. Thank you for your patience.